Today we will continue our discussion of the SN2 reaction by talking about some of the variables, some of the things in the reaction that we might change. And just in a generic sense, our SN2 reaction, we use a nucleophile, often supplying a lone pair. This bonds to an sp3 carbon, which there's a leaving group attached. The leaving group is going to leave. Remember, a characteristic of the SN2 reaction is that the nucleophile carbon bond forming event occurs simultaneously with the carbon leaving group bond breaking event. We'll see other mechanisms later where it's different. That's going to take us to a transition state, which has a partial bond between the nucleophile and the carbon and a partial bond between the carbon and the leaving group that's leaving. I'm not going to put charges here on our transition state. We might have delta minuses, delta pluses. But because I'm being generic and I don't know specifically what the nucleophile and leaving group are, I can't put charges on. And then we have our things attached. Call them R1, R2, R3, that are approximately in a plane perpendicular to this nucleophile carbon leaving group bond. And then that takes us up to our product and the leaving group. Now, as I mentioned last time, there are 4 things we're going to talk about in terms of variables, things that we might change. How would they influence the reaction? 2 of them we're going to talk about today. 2 of them we'll talk about on Wednesday. Today we're going to talk about the nucleophile, and we're going to talk about the leaving group. And we will see that how they operate is actually pretty similar. On Wednesday we will talk about the nature of the things attached to the carbon. We will also talk about some sort of what the solvent does in the reaction, what its role is, how its structure matters, and so forth. All right, so let's start by talking about changing the nature of the nucleophile. How might that matter? So number 1, nucleophile. To answer the question about how would changing the role of the nucleophile influence the reaction, we need to think about what's its role in the reaction. Here's a metaphor. I've never used this one before. See, it works. Imagine if we got rid of the chancellor. I'm not saying we should, right? I happen to like our current chancellor, but let's suppose he just went away. We'd have to understand the chancellor's role in the university to understand how his absence or resignation would influence what goes on in the university. Because there's lots of things, while the chancellor is the boss man, there's lots of things that he doesn't directly influence. Like, for example, how many parking spaces there are in Structure 2. He probably doesn't have a big say in that. So we need to understand the role of the nucleophile. Look at our mechanism, one-step mechanism. What is the role of the nucleophile? Imagine the exam question said, in 20 words or less, what is the role of the nucleophile in the reaction mechanism? What do you think? Go on, somebody's got an idea. No, just yell it out. Take the place of the leaving group? Okay, that's one way to think about it. When we talk about other mechanisms, you're going to see that it's not quite that way. It doesn't always take the place of the leaving group, but it's a good thought. Yeah. Donates electrons. Let's be a little bit better than that. How about shares electrons? Because it doesn't completely give them away. So let me differentiate the difference here. This piece of chalk, I've donated a piece of chalk to you. We're not sharing it. That's now your piece of chalk. And if you want, to not have your tuition go up so much at the end of the class, you'll put it back up here in the rack. On the other hand, if I was to walk back here and we both held this piece of chalk and we both used it together to lecture, that would be sharing, right? So the differentiation I'm trying to make here is this pair of electrons, which used to be the lone pair, is now shared in the bond. So it's sharing. It's providing the electrons that become the bond. It's just not outright donating. But it's a pretty close idea. But that's what the nucleophile does. It is the electron source. It is the electron provider. And if we want to think about this another way, we can think about this reaction in terms of the ability to be a nucleophile. The more willing the nucleophile is to share its electrons, the more philanthropic the nucleophile can be with its electrons, the better a nucleophile it is. Okay, so what controls how readily the nucleophile shares the electrons? It has to do with that electrons being accommodated, stabilized, made happy, etc. In other words, the happier this pair of electrons is to stay where it is, to not be shared, just to stay happy on the nucleophile. The happier it is, the better it's accommodated, the less inclined it is to be shared. And consequently, the nucleophile isn't as strong. Here's another metaphor. Lots of metaphors today. Imagine you are all by yourself. You're all lonely. You think about bars on a Friday night, but you go, nah, I'm going to study organic instead. How many of you have had those thoughts? And what was your choice? Organic. Which do you think would be more fun? Yeah, you can make arguments both ways, right? But you can stay home and drink while you're studying organic, right? So, and there's no cover charge for studying organic. So me, personally, I vote for organic, but easy choice in my case, I'm married. All right. So imagine this pair, it's all by itself, but wouldn't you really rather be in a committed relationship? But the happier you are at home, the less inclined you are to, let's say, go out on a bar, go out to a bar on Friday night. So the happier the electrons are here, the less inclined they are to go out and do other things. So we're going to talk about this in terms of the electron pair accommodation. Now, what kinds of things might influence the ability of the nucleophile to accommodate those pair of electrons and therefore might influence the nucleophile's ability, desire, driving force to share those electrons and make a new bond and be a nucleophile? Turns out we know the answer to this question, or at least we taught you the answer to this question back in Chem 14C. Do you remember in Chem 14C when we talked about basicity? Remember, if you had 14C with me, we talked about basicity in terms of accommodating electron pairs. And the reason we did that was because it makes it easier now. Here's how I want you to think about that. Imagine you have something X, has a pair of electrons, and it's going to use those electrons to make a bond to Y. And then whatever this bond that Y has is going to go away. In the case where X is a base, where Y is when Y is a hydrogen, we call X a base. When Y is a carbon group, like we're doing over here in our SN2 reaction, we call it a nucleophile. But the process is the same, pair of electrons making a new bond. So fundamentally, the things which control basicity also control nucleophilicity. Now, I say fundamentally, it's not a perfect parallel. And the reason it's not a perfect parallel is because basicity actually is not measured by rate. Basicity is measured by the position of an equilibrium. That's what pKa's are. And so consequently, this is a thermodynamic idea. It's controlled by delta G. Nucleophilicity, on the other hand, is controlled by rate. So this is a kinetic property. When we talk about nucleophilicity, we're talking about rate of reactions. So the fundamental thing which controls them is going to be similar, but it's not going to be exactly perfectly parallel. There are going to be cases where we have good bases that are also good nucleophiles and cases where we have good bases that aren't such good nucleophiles. All right, so let's go back and then talk about the factors that control nucleophilicity, i.e. the factors that control basicity. Does anybody remember what they are? First most important factor that carries the greatest amount of weight, not present all the time, but generally carried the great amount of weight when it came to controlling basicity and therefore controlling nucleophilicity is resonance. Now, if you didn't think resonance, you should probably get in the habit of doing that, because there are an awful lot of things that resonance has a significant impact on. You don't need to write this list down. Basicity, acidity, nucleophilicity, leaving group, all sorts of things. Huge, long list of things. And the reason for that is just generally resonance tends to carry a lot of weight. As a matter of fact, sometimes we jokingly say, what's the answer to every question in the organic chemistry universe? Resonance. Because so frequently it dominates over other things. So for example, if we had something up here you'd never seen before. For example, if I said, what's the single most important thing you think that controls the stability of carbocations? You're going, what the heck is a carbocation? Unless, of course, you've read ahead. But then it being an organic chemistry question, your answer would be resonance. If I said, what are you going to have in your pizza tonight? You would say resonance. And if you call up Domino's and say, give me extra resonance, they'll probably hang up on you. But nonetheless, it's the general answer. If you wake up in the middle of lecture and I'm pointing at you, I'm not saying that you're falling asleep, but if I'm pointing at you because I want an answer from you, you're waking up, the first word out of your mouth probably is resonance, or where am I? All right, resonance. Let's compare an example. Let us compare acetate ion versus ethoxide ion in terms of nucleophilicity. We're going to figure out which is the better nucleophile. Well, to do that, to look at any property, we have to have and how structure influences it, we have to have a good indication of exactly what the structure is. For this particular guy, acetate ion, we draw in some lone pairs. Is this an adequate representation of this structure? For some purposes, yeah. But is it reality? No, it is not reality. Reality is the resonance hybrid, and this is simply a single resonance contributor. So if we were to draw the other important contributor, that's this guy. Pi bond lone pairs switch places. If you're a little weak on resonance, good idea to go back and review that from 14C. We do a lot with resonance. And then down here for ethoxide ion, how is this one? What other resonance do we have? Nothing. This is all single bonds. Remember, resonance generally requires open octets, lone pairs, pi bonds, and this has none of them. So there's no other significant resonance contributors here. Now, of these two resonance contributors, which one should I use to represent, which one is the best representation of reality? Or is that a trick question? It's a trick question, because the best representation of reality is the resonance hybrid, the blending the average of these guys. So for acetate ion, that looks like this. There is a sharing of the negative charge of the two oxygens, a delocalization of those two pi electrons. That's what the dotted lines are. For ethoxide, we only have a single significant resonance contributor, and so consequently we can use that single resonance contributor to judge its structure. Now that we have best representations of structure, now we can make this nucleophilicity discussion. Nucleophilicity, we said, is about the ability to accommodate the electrons that we would share to make the new bond, that would make us happier, make the molecule, so the case where the electron pair is happier is going to be less nucleophilic. So in both of these cases, it's going to be the oxygens that are sharing the electrons to form the new bond. Now, I know that because the job of a nucleophile is to share electrons, so they generally come from where there happen to be a lot of them on the molecule. Lone pairs, formal negative charges, that's more electrons available, so that's generally where the seat of the nucleophilicity is. So it's either one of these oxygens in acetate or this oxygen in ethoxide. Now, which one of those two structures do you think the electrons that would be shared would be happier? Well, here's a way to think about it. Remember back in 14C, we talked about electron pairs, like little kids running around in the backyard? Remember that one? Let's talk about it like college students running around in an apartment. Here we have 6 college students. I can't count today, not enough coffee. 6 college students or 3 college students, if you want to think about pairs, whatever you'd like, together in an apartment, which is one room. It's like a dorm room, except it's a room, as opposed to a closet. Up here, the electrons that we would share, the pi bond electrons, let's say, are in a bigger place. They have more oxygens to run around on. So where do you think the electrons are happier? In acetate ion or in ethoxide? Top case, happier, or bottom case, happier? Top case, happier. More space to run around in. If the electrons are happier, they're less inclined to move out, to be shared. So which one of these two, top one or bottom one, acetate or ethoxide, which one of these two is the poorer nucleophile? Acetate. This is the poorer nucleophile because the electrons are more delocalized. They're more spread out. They're happier. In other words, acetate ion accommodates the electron pair better, and it's less inclined to find an extra place to live. So this is the better nucleophile. Exactly the same thing as we would find out if we were discussing basicity. Now, there's an alternate way, virtually identical way to think about that, and that's instead of thinking about electron pair accommodation, which doesn't work for some students, let's talk about this resonance circumstance. Here's acetate. Now, I'm going to use a single resonance contributor for this for mechanisms. As a matter of fact, most of the times in mechanisms, we use a single resonance contributor as opposed to the hybrid. Even though the hybrid is reality, the hybrid, because it has delocalized electrons, it just isn't as clear in a mechanism where the electrons are coming from. So we often just use a single contributor. So I want to do SN2 reactions with these two guys just to make this stability issue point. OCH3. So there's one SN2 product, and if we react this with methyl iodide, exact same SN2. All right, so we have two products. In both cases, methyl iodide, CH3I is the electrophile, so that's not the difference. If I didn't know any of this stuff over here about electron pair combination, and I wanted to compare the nucleophilicity of these guys based on this, one way I can do that is by looking at the change in resonance. Because resonance is something that molecules want to keep. Another metaphor. This is like the most metaphor-concentrated day of the entire quarter. Until next time when I think of even more. How many of you have money? This is a metaphor, honest to goodness. How many of you have money? You have money? Can I have 20 bucks?
Sure.
Really? You want to give me 20 bucks?
I can write your check.
Oh, that's giving me a check. That's not. I'm talking about American cash money, not yen, not lira, not pesos. I'd ask for Canadian, but you have to. I think right now it'd be even more than 20 American, right? 20 Canadian, and their money is prettier than ours. You want to give me money? Well, you're philanthropic. That doesn't work very well. But you're supposed to say, "No, I have my money and I want to keep it because I have to pay my tuition."
Absolutely not. I have to pay my tuition.
So she has to pay her tuition. She doesn't want to give me money because if you gave me money, you would be unhappy, right? Okay, now let's change that. Imagine you didn't have any money because you just paid your tuition. You didn't have any money and then some, right? Because you've just paid your tuition. Are you happy or not? No. Would you like to have some money to fill that void? Absolutely. So the point I'm trying to make here is that resonance for molecules, right? This is like an SAT question. Resonance is to molecules as money is to college students. If you have money, you would like to keep it. Unlike our volunteer here in the front. Thank you for being philanthropic. If you have money, you would like to keep it. If you don't have money, you would like to get it, right? How many of you don't have money but would like to get some? How many of you think money is completely useless? We should go back to a barter system. So your tuition, so instead of having to pay 100 chickens now for the quarter, your tuition's 132 chickens. Barter system? Go to Wikipedia and look it up. All right, anyways. So the point I'm trying to make is molecules, money is like resonance. Molecules, if they have resonance, they'd like to keep it. If they don't have resonance, they'd like to get it. So how does that work here? Acetate ion, as we saw, has wonderful resonance. It has two contributors that are virtually identical except for the position of the electrons, what we call degenerate. This is the best kind of resonance you can have, equal contributors. Acetate ion, very nice resonance. The ester that we produce from that still has resonance. And you can draw the contributors and convince yourself of that. But it doesn't have as many significant contributors as acetate ion does. So when this reaction occurs, it occurs at the expense of some resonance. Money goes away. In the bottom case, ethoxide has no resonance, and the product, ethyl methyl ether, also has no resonance. So there's no loss of resonance. And this loss of resonance is felt in the transition state, the thing that controls the rate of the reaction. It's felt in the transition state. It's an extra energy price you have to pay. It's like if you want to go see a movie, and I'm not talking about Avatar, I'm just talking about like a movie, right? You know, some movie from the 80s, that kind of thing. And you can see it for free. You go, okay, fine, I got nothing better to do. I'm going to go see this movie. But now but on the other hand, you got to go pay $10 for it. Even, are you more inclined to go see the movie if you have to pay for it? No, you're probably less inclined. It's the same thing here with resonance. So you can view this resonance effect on nucleophilicity either way, both ways. They're both contributing factors. If resonance delocalizes the electrons that are going to be shared, makes the nucleophile more stable, less inclined to react. If resonance gets lost or decreased during the reaction, that inhibits the rate, slows it down because it makes a higher energy price. Both arguments work together. Now, before we leave resonance, I'm going to leave you with one reminder that I said back in 14C, remind you of again here. In 14C, we talked about resonance and basicity, and I reminded you that not every case where resonance occurs causes a decrease in basicity. There are plenty of cases where there's resonance and no change. It doesn't influence basicity. And there are a few cases, they're uncommon, but they're out there, where resonance enhances basicity. And it does so by importing electron density from elsewhere in the molecule instead of spreading it out. Exactly the same thing applies for nucleophilicity. Just because a nucleophile has resonance does not necessarily mean its nucleophilicity is decreased. Sometimes the resonance doesn't matter at all. Sometimes, rarely, it enhances it. All right, let's talk about another factor. I'll leave this up here. Next most important factor carries a little bit less weight than resonance. Anybody remember? Somebody said it. I heard it over here in the cheap seats. Somebody said it. No? Okay. Atomic radius. Atomic radius. So as an example of this, let's talk about this guy, methane thiolate versus methoxide. Now, when these guys participate in SN2 reactions, let's say, let's just use methyl iodide again. Methyl iodide. So it is the sulfur in this case that's providing the electrons. And again, I can make a guess at that because it's the sulfur is the only place where there are lone pairs, and it's the sulfur is where the negative charge is. So that tells us in the molecule that's where the available electron density is. And that's what nucleophiles do. They share electrons, right? It's like when you have to pay a bill, don't you find your credit card account that's got available credit? That's the same thing up here. You need to share electrons. You look for where the electrons are. All right, so sulfur versus oxygen. Now, before we want to compare the nucleophilicity of these guys, but before we reinvent the wheel, so to speak, and introduce some new idea, let's talk about what we already know, and that's resonance. Pretty simple in these cases. Here's a case where the difference in resonance between these two, there's no difference in resonance. In other words, neither has resonance. Remember, when you're making comparisons, look for differences. All right. So the next thing we have up here is atomic radius. This is the new thing. Sulfur is larger than oxygen. How should that matter? Well, let's go back to living in the dorm room. Let us imagine that you live in the dorm room with your, let's say this is you. And you live in the dorm room with your 5 other roommates. Right? Chem 14D student and the 5 electrons. That sounds like the name of a band. Do you want to live in... Now, you're stuck in one room because you have no resonance. This is like not quite a warehouse. This is like a gymnasium. This is a typical dorm room. How do I know that? Periodic table. Oxygen's in the second row. Sulfur's in the third row. As you move down in rows, you add another shell of electrons, which means the atoms get bigger. And we're talking about the valence electrons, not the core electrons. They really have nothing to do with this. It's the valence electrons, the surface electrons. Sulfur's a bigger atom. The electrons live in a bigger space. Would you rather live, as a college student, in a bigger room or a little room? Remember, you're stuck in one room. You've got a bunch of roommates who, for this metaphor to work, you don't particularly like, because after all, they're electrons. If you're an electron, they're an electron, you repel each other. Probably because they have, undesirable personal habits or something. Would you rather live in the bigger room or the smaller room? Bigger room, right? You have more room to run around and get away from the people you don't like. Exact same thing with electrons. Electrons are happier on sulfur because they're more spread out. They have more space to get away from their neighbors, and consequently, better electron pair accommodation on sulfur because it's bigger, less inclined, less inclination to have to go out. So this is the better nucleophile because of the larger atomic radius of sulfur. Now, if you've done a little bit of studying on the subject, you might go, wait a minute, Dr. H, you wrote the wrong answer. Like I said, not enough coffee. Okay, blame it on budget cuts. Not enough coffee for me. Better nucleophile. All right, now, if you've studied a little bit about nucleophilicity or read another textbook, or maybe you've taken this kind of course at another university, you may have heard a little bit about polarizability and how that matters, and that you might be thinking, but shouldn't the sulfur nucleophile be the better nucleophile because it is more polarizable? And the answer to that question is yes, but. And I say yes, but because, number one, you have to think about solvents, which we're not talking about here. We'll get to those later. Number two, polarizability is a useful idea, but it's not going to be necessary at our simple thought level. Ignoring polarizability gives you a theory for nucleophilicity which gets it right maybe 90% of the time. How many other things do you know that are very simple that are right 90% of the time? That's what I thought. Baseball players. How much would a baseball player get paid if they got on base 90% of the time? And didn't do drugs. That kind of thing, right? So 90% is pretty good. So we're going to ignore polarizability. If you know how it works and you can invoke it and get the right answer, that's great. But it really also only matters at the extremes anyways. So for our purposes, that's a better nucleophile because the atom is smaller. Let us do a third example. Back in basicity, going down in the increasing order of preference, resonance, atomic radius, the next thing we talked about was electronegativity. This one's kind of straightforward. So we'll talk about hydroxide and fluoride is the case here. So if we were to compare the nucleophilicity of these guys, again, if we were going to react them, let's say, with methyl iodide. So there is the reaction illustrated with hydroxide, same kind of thing with fluoride. We can see from this, as we've seen several times before, that the role of the nucleophile is to share electrons. A good nucleophile is philanthropic. It likes to share its electrons. Well, what is electronegativity? Electronegativity is a measure of electron greediness. High electronegativity means strong attraction for electrons. Now, to be fair, that's not quite completely rigorous. Linus Pauling's probably going, oh, I wish they'd quit talking about electronegativity that way because that's not the way I defined it. And that's true, but our definition works pretty well. So I'm sorry, Professor Pauling, we're simplifying things. But we're thinking about it in terms of electron attraction. So compare the electron attraction for oxygen. What's its electronegativity? You may remember what the number is. These numbers are useful. 3.5, second most electronegative atom on the periodic table. Fluorine's electronegativity is 4.0. That means that fluorine attracts electrons or holds electrons more readily. It is higher electronegativity for fluorine, which means it is less philanthropic, less inclined to share. So between the two of these, hydroxide and fluoride, which is the better nucleophile? Hydroxide better or fluoride better? Remember, electronegativity is high electronegativity is greediness, and a nucleophile is supposed to share. So this does a better job of sharing. It's still not all that terribly inclined to share, but it's a better job. So this is the better nucleophile. Now, in comparing atomic radius and electronegativity, you might say, whoa, whoa, whoa. There's an inconsistency here. Here you said that methoxide is the better nucleophile than methane thiolate, but oxygen's more electronegative than sulfur. What's going on here? What's going on is the fact that Mother Nature generally says that atomic radius carries more weight than electronegativity when you have to compare the two. So that's not always true, but it's true often enough that it's a pretty good guess. In this particular case, atomic radius is not an issue, because when you're comparing elements in the same row of the periodic table, their size is generally the same. In other words, if we have a periodic table, boron, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's a portion of the periodic table. And we can throw in sulfur and phosphorus, and if you'd like. If you're comparing the business end, so to speak, of the nucleophile, the portion of the nucleophile that's sharing the electrons, and you're comparing within the same row, then it is the atomic radius that matters. If you are comparing within the column, on the other hand, where atomic radius charges, whoops, See what happens when you don't pay enough tuition? You get like these second-rate lecturers that just aren't thinking. All right, so when you're comparing in the same row, where the atomic radius changes only slightly, because you're not adding another shell of electrons, but the electronegativity charge changes are fairly large, it is electronegativity that carries the day. When you're comparing in the same column, where electronegativity is changing, that's true, but atomic radius is changing very significantly. Second row, third row, fourth row, fifth row, iodine's pretty big. Then we worry about atomic size differences. That's what matters. Before we leave these two factors, one more issue I want to mention on this list. And this is an atomic radius issue, so I'm jumping back very slightly. I want to remind you that when we're talking about atomic radius, it is the radius only of the atom that's doing the sharing. In other words, if I was to compare the nucleophilicity of these two guys, methoxide and tertiary butoxide, if I was to compare these two guys, it's the O minus that's the business end. That's where the negative charge, that's where the lone pairs are. And they're both oxygen atoms. There's no resonance delocalization. There's no difference in electronegativity. There's no difference in atomic radius. They're all the same atoms in the same functional group. That means that we're going to say that their nucleophilicity is virtually identical. It's not exactly precisely equal, but it's close enough to be equal at our introductory level of analysis. Depending upon what other factors you dredge up, you might make arguments one way or the other. But for the most part, pretty much equal nucleophilicity because the business end is the same. All right, so the fourth factor we're going to talk about a total of 5 here. The fourth factor that we might consider has our decreasing order of influence has been resonance, atomic radius, electronegativity. Even less influential is inductive effect. Let's, for the purpose of this, I'm going to use actually the same example I used when we talked about basis. I'm going to work the same here. Let us suppose I want to compare the nucleophilicity of these two carboxylate anions. All right, so let's go through our series of factors. What do we know? We start with resonance. Does this guy have resonance? Yes. Does this have resonance? Yes. Is their resonance the same? Hint. Is their resonance the same? Yeah, they're the same assemblage of atoms, so they have the same resonance because they have the same drop the F-bomb. It's okay. You're just being videocast. Come on, who's going to drop the F-bomb here? Bree, do you want to drop the F-bomb? Not really? Well, gosh darn it, they have the same functional group. That's the organic F-bomb. Feel free to use it all you'd like. So when you get frustrated studying organic, you can go, gosh darn it, functional group. Because they have the same functional groups. They have the same atoms, the same lone pairs, the same formal charges, therefore the same resonance. And because they have the same atoms bonding lone pairs, formal charge, and so forth, that means they also have the same atomic radius on the business end, and they have the same electronegativity. So what is different between these two guys? It's CH3 versus CF3. Does that influence the electron density, the electron accommodation out here? Well, when you think of that, what do you think of fluorine? It's the difference, hydrogen versus fluorine. Fluorine's different than elements in a lot of ways, but what's one thing that it's the champion at? Electronegativity. Now, this is not directly an electronegativity effect because it's not, these oxygens have the same electronegativity, but it is kind of an electronegativity, but at a distance effect. You can think of inductive effect kind of as electronegativity, remote electronegativity, if you will. These fluorines, being highly electronegative, are taking electron density away from their neighbors. And they're doing that, they're pulling electron density from everywhere in space around towards them. So pulling towards itself. Methyl groups don't do that. As a matter of fact, methyl groups are weak electron donors. We'll see more of that later, but they tend to be, they're kind of weak. They do it, but they're not really powerful at it. CF3, on the other hand, is a pretty good electron withdrawing group. So sometimes we say EDG, electron donating group, and Wg electron withdrawing group. So what does that do? If I'm taking electron density away from the CO2 minus portion, if I'm taking electron density away from the portion of the molecule that's supposed to share electron density, what does that do to nucleophilicity? In other words, which one of these is the better nucleophile, acetate or trifluoroacetate? Better nucleophile, which one? Top or bottom? Top. This is the better nucleophile. Because this inductive effect of the CF3 is taking electron density away from the CO2 minus. Now, this is an electron withdrawing inductive effect here that mattered. There are plenty of those out there. There are also electron donating inductive effects. The methyl is doing that very weakly. For the most part, what you will see with nucleophilicity, as you saw with basicity, is that electron withdrawing effects are what you're seeing. Occasionally, there's electron donating, but most of the time, the effect is electron withdrawing. All right, there's one factor left over, which we call the X factor. And we call this the X factor because this factor left over, unlike the other four. The other four we've talked about resonance, atomic radius, electronegativity, inductive effect. The vast majority of time have that particular sequence of influence. In other words, resonance usually beats atomic radius usually beats electronegativity, and so forth. This last factor, the X factor, it can be very powerful, but it doesn't usually fit in that sequence in the same place all the time. Sometimes this factor has more power than resonance, sometimes less. Sometimes more than electronegativity and less than resonance. Sometimes it's other places. And the X factor is, anybody remember? Formal charge. This is also, I think, another factor relatively easy to understand how it influences nucleophilicity. Let's suppose we were comparing hydroxide and water. Again, I'll use them in an SN2 reaction. There's hydroxide, and water can do the same kind of thing. It is the oxygen, in both cases, that would be supplying the electrons. Both cases, that's where the lone pairs are, and in the case of hydroxide, that's where the negative charge is. Now, if we were to compare the nucleophilicity of these guys, once again, go through the list of factors. But it's both oxygens without resonance, same electronegativity, same atomic radius, lack of resonance in all cases, no inductive effects, withdrawing or donating to matter. So what's left over? Negative charge versus no negative charge. What's a formal negative charge mean? I mean, what does it really mean? There's a way you can express it and calculate it. But what formal charge really means is that this atom has more electrons than it really needs. It has excess electrons. So a formal negative charge means, compared to a neutral atom, more electrons to share. And if nucleophilicity is about sharing electrons, well, hydroxide is the better nucleophile because it has the formal negative charge, because it has more electrons. There's another way to look at this, too. Let me write the product of this reaction, and maybe that will help you see it. That's the top one. And I'm going to slide the water over here just so I have more room to write this. So we have two products. If hydroxide is the nucleophile, methyl alcohol is the product. If water is the nucleophile, this thing, which is called an oxonium ion, is the product. Now, atoms like to be formal charge neutral. They would rather be neutral than negative or positive. So here's another way to look at this. When hydroxide reacts in the SN2 reaction, it goes from negative to neutral. That's good. It's getting rid of excess electrons. It's happy. It's neutral. When water acts as the nucleophile and it goes to make this oxonium ion, it goes from having neutral to positive. Doesn't like that. It would rather be neutral. So an alternate way to think about how formal charge works is to think about how the formal charge changes. Negative or positive to neutral is good. Neutral to negative or positive is bad. So here, good change because we're getting quenching charge. Here, not so good change because we're creating charge. All right, so those are the 5 factors we're going to talk about working pretty much exactly the same way for nucleophilicity as they do for basicity. Now, let's shift to, we talked about nucleophilicity. Now let's talk about the leaving group. All right, so number 2, leaving group. I could. I'm not going to. I could send you at home at this point and say, okay, we already know how to do leaving groups, so go home and write 100 words on how leaving group works because you already know how to do it. But I'm not, because we have 10 minutes left or 9 minutes left to go. And I know you probably won't do it anyway. I'm sorry, I'm too cynical. All right. Let's ask exactly the same question. If we want to know how changing the structure of the leaving group influences the rate of the reaction, we have to ask ourselves, what is the role of the leaving group in the reaction? Here we go. Here's our mechanism. What does the leaving group do besides leave? Definition of leaving group says it leaves with the electron pair. It takes the electron pair with it. That sounds like the opposite of something we just finished talking about. The role of a nucleophile is to form a bond by sharing electrons. The role of the leaving group is to break a bond by taking electrons with it. Same kind of idea, just simply opposite direction. So you might think, oh, then let's see. If better nucleophiles were ones that wanted to share electrons because they didn't accommodate them very well, then wouldn't the best leaving groups be the ones that would accommodate electrons? Because they say, come here, boy, come on. And they want to leave, right? They want to take them away. And that's exactly true. So the best leaving groups are good at that electron accommodation. Now, as a corollary, we might say, does that mean that there's an exact reverse? The things that are good nucleophiles are bad leaving groups? And the things that are bad nucleophiles are good leaving groups? Almost. Not perfect, but it's a pretty good correlation. Now, instead of going through all these factors, as we did for nucleophilicity, what we're going to do here is we're going to turn to our lecture supplement. We were on page 4. And look at a list of leaving groups and try to understand why they are categorized the way they are. The reason we can't do this for nucleophilicity is because the structure of nucleophiles just vary too much, and the list would be very long. It turns out the list of common leaving groups is not very long. All right, let's see if this is going to work today. All right, there we go. But you have this in front of you anyways. All right, so this is a scale of leaving groups. We have really, really good leaving groups. We have okay leaving groups. We have leaving groups that are kind of clingy, since we were using the relationship idea before. We have a group of leaving groups that two groups of leaving groups that only leave under special circumstances. And then finally, we have leaving groups that basically never leave. So what I want to do here is look at these groups and try to understand what makes some of them good leaving groups. Let's start with, let's do iodide. I think that's the easier one first. So here's iodide ion. And this is the structure of the leaving group after it's left. Here's what it looks like when it's leaving. And I know it's not shown as an SN2 reaction, but it doesn't have to be, because a leaving group is a leaving group. It doesn't matter what reaction it's in. So let's look at iodide. It's an excellent leaving group. As a matter of fact, iodide is one of the best leaving groups you will ever encounter. What is it about iodide? Think about our 5 factors. What is it about iodide, if you had to pick one thing that makes it good? If you were hunting for a new place to live and you went, say, iodide, that's a nice place to live. I want to move into there. What would it be that's attracting you? Probably not the new marble countertops in the kitchen. What's attracting you? Big space. Iodide's big. Yes, 1 point for me. Iodide is big. That's the principal reason why it's a pretty good leaving group. What about sulfonates? Now, sulfonates are a group of leaving groups where the R is different things. It could be a methyl. It could be a CF3. It could be a benzene ring. Those are the 3 most common ones. So here's what sulfonate looks like. It looks kind of like sulfuric acid case. What is it about the sulfonate here? I've got to slide that down a little. What is it about the sulfonate, do you think, of our 5 factors, if you had to pick one that makes it such a wonderful leaving group? Resonance. When it leaves, so it goes from having no really great, it's 1 good resonance contributor to having 3 good resonance contributors. Its resonance circumstance is improved when it leaves. So those are the best. And if you have a CF3 out here as the R group, that's about as good a leaving group in the sulfonates as you can get, because the CF3 group, like we saw up here, provides an inductive effect on electron withdrawing, which further stabilizes that negative charge. All right, now in the middle, we have a group of leaving groups that are they're pretty close in terms of their ability to leave. They're not the best, but they'll do just fine. So we have bromide, chloride, water. and an alcohol. So let's start with bromide and chloride. These are not as good as iodide. Why do you think that would be? They're smaller, right? Bromide's a little bit bigger than chloride, so bromide has an advantage in that way. But bromide has a disadvantage over chloride. What is that? Think of all the factors. Resonance, atomic radius, electronegativity, inductive effect, formal charge. In what way does... so bromide has an advantage because of size, but it has a disadvantage between these two because of electronegativity, right? Chlorine holds on to its electrons a little better. So between those kind of balance out, and bromide and chloride are about the same. Bromide's usually considered to be a little bit better than chloride. Between water and methanol, these are virtually identical because the difference in atomic radius is the same, or there's no difference in atomic radius. There's no difference in electronegativity on the oxygen, et cetera, et cetera. So these guys, they're about equal. Now, these two guys, water and methanol, have an advantage in terms of leaving group over bromide and chloride. What do you think that is? Formal charge. When these oxygens, with a positive charge to begin with, when they leave, they accept the pair of electrons that used to be the carbon leaving group bond. That quenches the positive charge, and so they're neutral. That's a good thing. So all of these guys have some good things, some not so good things. Now down here in the next section, we have rarely leave. These leave only under pretty much special circumstances. We basically really shouldn't expect them to be leaving groups too often. One is fluoride. What do you think the major issue with fluoride is? You sure? It's got really high electronegativity. It's like you move into an apartment, you're looking at an apartment and going, wow, I love the wallpaper in this one room. That's a closet. It's really nicely decorated, and the rent's great because it's only a closet. That's what fluoride is. Highly electronegative. Electrons are very happy to be on fluoride, but they don't want to move in because it's so tiny. All right, and then the amine case, I'll leave that one for you to contemplate on your own. The next group we have leave only under special circumstances. In other words, they are not leaving groups until we define the circumstances under which they leave, which we will do later on in the quarter. So alkoxides and hydroxides, those are about equal. And the same thing with nitrogen anions, nitranions. Down here, we're almost done with this. Down here we have H minus hydride ion. Hydride ion is a leaving group only in one reaction. That reaction is called the Chi-Chi-Bobbin reaction, which if you're really good, we'll tell you about near the end of the quarter. What is it about hydride that should make it a lousy leaving group? Well, it's bad in almost every single way you can think of. No resonance stabilization of the electrons that it's gotten. Really tiny atomic radius. Not great electronegativity, and it would leave with a formal negative charge, and it has no inductive effect to help us. So this is like moving into a refrigerator box under the freeway. There's just nothing good about it. The very last things are carbanions. That's carbon anions, where the negative charge on the carbon has no special stabilization, no resonance, etc. They simply don't leave. A methyl group, for an example, never ever in any reactions is ever a leaving group. Now, what we're going to do, I want you to think about the parallels between nucleophilicity and leaving group. And on Monday, what's the next day? Wednesday. Not enough coffee. On Wednesday, we're going to talk about the things around the carbon, the R groups, as well as the effective solvent. So you might want to read ahead on that.